Thank you. I see we're going to be here a while. Yeah, so I lost my voice, but not completely, so we'll do. So I don't know, somewhere before the summer when I was working on this project, and it was mostly still something we were planning to do, I expected that, well, by October, I'll probably have something ready. So I submitted a small talk to a small local conference. My talk got accepted. The next day, I got an email from the organizers if I would mind if they turn it into a keynote, because nobody would want to speak in the other room anyway. So then I got a little nervous. Then the software, of course, took longer to write. And now my boss is sitting here on the first row. So without further ado, so our claim, as the title says, structured RAG is better than RAG. We believe that structured RAG is an improvement over classic RAG, and it has advantages like longer conversations, it can handle, it can be faster, it can be more precise, I'm very convinced of that, and it can handle more complex queries with the right prompting. It's actually mostly not my work, but Stephen Luco and Umesh Madan. Stephen is here. Umesh couldn't make it. I did the Python port, and I re-architected the storage approach for a SQL. And then Umesh and Rob also helped with preparing the demos. So if something's wrong with the demos, I can blame it on them. So classic RAG. Well, why do we need this? Agents need memory, whether it's a chatbot or something more structured. And agents can use memory both for past interactions. Wouldn't it be lovely if I could just say, well, 2 weeks ago, or maybe half a year ago, we had this interesting conversation about how chemists are now using software, and in particular Python. What did we talk about? Who was in that conversation? Another thing, of course, is retrieving documents, because agents usually have access to a large collection of documents, like everything that you ever sort of found in an attachment, if it was an email or was sent around, needs to be retrievable. So classic RAG uses something called embeddings. An embedding of a text is like a 1,500 or more dimensional vector of floats between, I think, -1 and +1. And you get that embedding by making a call to a server. That call's pretty fast, and you can batch it, but you have to go to the LLM provider to get the embedding. So Rob wrote a nice diagram for me. I don't know if everybody can read that. That's a little small, but I think it will work. Hello, I wish to register a complaint. Hello, miss? So that's a line of a well-known skit that we want to be able to recall later. Maybe we want to recall the whole skit. So we send this to an embedding model. That's an RPC call to the wild internet. And the embedding model sends us back this long vector. I didn't show the whole vector. NumPy wouldn't either. But it's lots of numbers. And that is actually the first and last numbers of the embedding that ChatGPT produced for this exact sentence. And I don't know why everything has negative coordinates. Somewhere in the middle, there must be some positive ones. So we store that vector in a vector database, which is basically a long list of vectors plus pointers to data. Now, each vector represents a point in 1,500 plus dimensional space. Let's call it n-dimensional. We see very schematically in this little diagram here. Oh, I have no pointer, that's fine. We see the orange ball representing the newly added vector. And somewhere there's also a piece of storage where, hello, I wish to register a complaint is being stored, of course. So to find something back in a vector database, like the question, what's the matter with the parrot? Again, you send your question to the same embedding servers. You get another vector back. Then you have your n-dimensional space with lots of vectors representing points in there. Now, what you want to do is find which vectors are closest to your question, because those are most likely to contain useful information for getting the answer. So how do you do that? Well, mathematically, it's simple. You do the dot product of each of the vectors in the vector database, which could be millions, with this same source vector, question vector. So that's, with NumPy you can do that, although a million vectors would take like 6 gigabytes of space. Because one vector, if you used 4-byte floating point numbers, is 6 kilobytes. So that's not nothing. It's a lot more than the original sentence. So now you have, if there were millions of vectors, you have millions of correlation numbers or similarities, each one single floating point number between -1 and 1. So very schematically, that tells us that we're closer to some vectors than others. You want to keep the top n. For the diagram, I used 2 for n. So we have the two best matches, the two closest vectors in that entire vector database. Realistically, we would probably use 25 or 50 or so. And we find those two little green balls next to the orange ball are, in fact, its closest neighbors, or the most similar, as we say. So there are many books that explain more about RAG, but this is all that I wanted to fit on a slide. So pros, it's well understood, well, except when you go to sort of really large vector databases and you have to do some kind of clustering to be able to compute the answer in finite time. Even for a million, you probably want to sort of at least split that between multiple CPUs and possibly multiple machines and multiple disks and all that. The downside is vector databases, because they have all that actual complexity, they're expensive, they're complicated. The vectors take up lots of space, much more than the inputs in many cases. And if you try to optimize how many vectors you have, you might say, oh, I'll just do one embedding for an entire document. Well, guess what? You get very mushy results, because a document often mentions very many different topics. It mentions the word performance, it mentions the word tests, a whole bunch of maybe fairly low-ranking hits, because you can find them in anything. But it's hard to find things that are relevant this way. I've heard the number about 60% recall for vector databases. So we hope that structured RAG does much better. In structured RAG, instead of using an embedding, we use a bigger gun. Although the bigger gun is being made smaller and cheaper as we speak, of course. And we encourage the industry to keep doing that. So the LLM is given the text, and it extracts knowledge from that text. And for knowledge, you should imagine entities, actions, topics, maybe other things like relationships, although you can model those with entities and actions already. And we store the knowledge, which is usually a small record or a little tree of information. Like you have an entity and it has a name and it has properties and facets and possibly a time range. So you store this in a classic database. In our case, we just put it in SQL, which is easily queried. And before we get to the querying, let's show the same thing for the ingestion here. This parrot wouldn't boom if you put 4,000 volts through it. It's bleeding demised, literal quote. So now we're going to send that to an LLM, but we don't send just this to the LLM. We give it a very specific prompt, and the prompt says generate JSON, and then we give it a schema. And in our case, because we like TypeScript in some sense, well, TypeScript is at the origin of the whole project. Excuse me, here we go. Anyway, the schema is actually expressed as a set of TypeScript types and interfaces. So we send all that to the LLM, and it comes back with those topics, those entities, topics, actions. I can barely read this on my own slide, but a parrot is definitely an entity that you'll find there. Topic, def, Voom is the only word really there that's worth storing. Then we send this plus the original query. Well, sorry, I was on the query, but we're not there yet. We store those topics, entities, and actions in our SQL database. With a particular interesting schema, and we also store the original string there. So now we want to query that database and find answers to our questions. So to query, again, we use an LLM to turn the user's question into a database query, and that doesn't mean that we make it generate SQL. We make it generate some JSON that represents a query that you can translate to SQL or to many other databases if you feel like it. And then we have another LLM that takes the data and turns it into a human-readable answer, which actually a classic RAG would also need. So here's the query pipeline. Let's ask what's wrong with a parrot. Again, we send this to an LLM together with a prompt that says, generate JSON that follows this schema. It's a different schema, of course, than we use for ingestion. The LLM comes back with a query. Then I skip a few steps. Then we query the database. Out of the database come those entities and so on. Knowledge nuggets is the official term from now on. Then we send that, which is just a bunch of database records, really, plus the original question, of course, that the user asked and wanted to get an answer to. And here we don't give a schema because we actually want natural English back from the LLM. But we says, given the knowledge, so we now input JSON to the LLM and the original question, and the LLM turns that into something useful like, the parrot is deceased. We'll see that question. We can do that question during demo. So if we evaluate structured RAG, we have better recall and precision because we use this extracted knowledge. And the extracted knowledge, the knowledge nuggets, are much more precise than an embedding vector can ever be. Because there's nowhere in an embedding vector where you can say, here it says grandmother. You just see if your vector is close to the vector for grandmother, and you may be lucky or you may not be lucky. We can scale this to any size, basically. And because we index everything ahead of time, what we have to do for querying the database is actually much less work than what a vector database needs to do for every query. With a vector database, basically all the work happens at query time. I'm improvising now. While with structured RAG, more of the work happens at ingestion time, which means that if, assuming you ingest things once and you ask questions many, many times, this would give us a speed advantage, performance advantage. There are also things that you can do at query time, like doing inference over knowledge nuggets. For example, if we know that Michael Palin is an artist, then we can infer that Michael Palin is a person, not a super difficult inference. But that helps with when you have a question like, what people did we talk about yesterday? And there's also knowledge that you can extract without help of an LLM. Like if you were to extract, to ingest email messages, you don't need an LLM to read the from and the to lines and a few other bits of metadata. But in all fairness, bulk ingestion is slower. So now there's a demo that I promised. I have to guess which window that is. No, that's the wrong one. Here we are. Okay. So I have to switch. Dang it. I don't know how to do that. Okay, I have to get, I go back here. And here we are. Okay, so I collected my, what? Oh, I have to move this to the other window, I betcha. And it won't let me be, oh. That's what I did.
You have to start sharing again and then drag it over.
If I bring the slides up, I'm sure it will work again.
No, reseat it. There you go.
Yeah. Okay. So I don't know how to deal with this technical problem. Is there anyone from the AV? Is there an AV team who can help?
So just drag it to the other window. You're an extended desktop, right? So drag it to the right. And you'll see it appear on the TV in front of you.
Sorry. I didn't hear that. Can someone repeat that?
So drag it to the right, and you'll see it on the screen in front of you. It's the extended desktop.
Yeah, that I figured out. But I don't know yet how I can take my terminal window and present it. Dragging to the right. Oh, great. And now, so I have a problem now because now I can't see what I typed. Wow. Well, I'll try to type blind or something. So the thing takes a few minutes to start up anyway. Shall I make the font bigger? Because I think it reverted to a pretty small font. How about that? Okay. So let's start with the question everybody wants to know if it works. Wow. Wow. It knows. Now I'm improvising. Yeah, okay, giving up on the bruises. What else do I have? No, that's not in. That's from a movie, not from the sketches. No, I could, but I'd still be indexing. No, yeah, give up on the bruises. Let's go to the more obscure stuff. Know that my user interface here does not have conversation history itself, so we're not eating our own dog food yet. So I can't use it to refer to the albatross that I mentioned in the previous question, but it does know what the man says about the albatross. What's a chalk eyes? Now that I know this will fail because there is nothing about chalk eyes. And look how sort of careful it explains why it failed. Maybe I should switch to the other demo. Hopefully the setup will be quicker. Oh, dang, I lost it. Okay, well, that's not a problem. All I have to do is change the database. Yep, there we go. This demo is even newer than the Monty Python demo. I indexed about 500 messages from my own email that I collected a few days ago. Let's try something. Well, I'll get to that. That is a good question. In this demo, I have to use send instead of say because of the way the indexing is done. Okay, well, Colesbury made a commit. That's good. That seems to be one of his major activities. Yeah. That should work, but I've never tried it before. Okay. Thanks for all those emails you answered, Chris. Is the date wrong? Ah! It probably took the date from the message or something. That handling dates is definitely still an ongoing issue. I do have a few more slides, so now my question is, how do I get rid of that window? Okay. But we started over, that's not good. Yeah, but then I have to go through the Shift F5. Boom! Okay, so I have a little bit more. This is open source. You can download it now. You can pip install it from PyBay. It's version 0.3.0, which is very early alpha in my mind. It doesn't work unless you have an OpenAI key. Generalizing it to other providers is left as an exercise for the reader. And if you get anywhere there, I'd love a contribution. I don't know how many of you saw Glyph's talk at 10 a.m. in this room, but the key thing is to get contributors. So a very simple program. Well, this is really only half a program that shows you how to ingest stuff. So you have to do a few imports. The key line is here. You call create conversation. You give it a database, file name, and a class. It would be nice if that class had a default, but currently it doesn't. So that's why you have to import it. No, but you need that class anyway, because you need to provide the actual ingestion code with a list of messages of a particular type. And transcript message is a subclass of the base interface for the message type. And the base interface is abstract, so you could write your own easily, and we'll eventually document that. So you stick the text in, so chunk is for chunk and speaker in, and here's a bunch of dots, and that should be a lot of dots because you basically have to write at least 20 lines of code or so to get something interesting from a file that you want to ingest. And if you have multi-Python scripts and you've made them up as transcripts in the web VTT format, we happen to have a driver for that, which is, I don't know, 100 or 200 lines. If you have other formats, you probably have to write your own driver. We have a very early pre-alpha email ingester. So the one call you make is just once you have produced your list of messages, where you get to do a bunch of work, you just call this add messages with indexing method on the conversation object, which really is a big wrapper around a database. This call is our very high-level ingestion API. The nice thing about it, it's also a transaction. So all those messages are either added to the database or none of them are added to the database. And when they're added and the transaction succeeds, they've also all been indexed. There are more options, but not everything is super relevant. So there's also a very simple example of how you query stuff. You just use create conversation with the same database file and class. Then you have a string representing some question that the user asks, and then you make the call conversation.query with your question, which is just a plain string, and it comes back with a plain string, and you can print that. And that's it. I have a bunch of links. Here's our repo. There are a few docs, contributions welcome. We're on PyBay, but all you have to know about that is the name type agent, which you give to pip or UV or your favorite. We haven't written papers yet, but we really should. So that's all I have. Wow. We can have questions.
Okay. Yeah, thank you. So any questions for Guido about structured RAG in the front?
Thank you for a great talk, Guido. I'm from Neo4j, in a graph database, and it looks like since you have the schema for the messages, it would be easy to create a graph out of them. For instance, connecting names. Have you thought about adding graph rag on top of structured rag?
I'm sorry, the acoustics do not help.
So we're at Neo4j building graph rag, basically connecting different chunks with links in a graph. And since you have already structure for the nodes, how easy would it be to build a graph layer on top of this, and have you thought about adding graph?
He's asking about graph rag.
Okay. So we're working with Jonathan, and who has the graph rag project at MSR, and they're pretty complementary things. The key thing is this thing allows for incremental indexing. So as the conversation is going on, you can be adding. Because you don't have to run clustering algorithms, you can keep an up-to-date index in an ongoing conversation. So if you are talking to an agent and then 10 minutes later you want to say, hey, weren't we just talking about some song? Can you play that song again? It's available because you don't have to do all the clustering algorithms and sophisticated summarization like you do with GraphRag. So incremental is one big difference. And then the other thing is that we extract topics directly using the LLM. So we extract a hierarchy of topics. And that's a lot like forming the clusters in the GraphRag case. And I think the best thing to do is to play with both of them for your application and empirically decide which gives you better topics. You know, it kind of depends. Like in the case of GraphRag, you're inducing topics from a very disparate set of details, and so it can actually create topics that would be hard for the LLM to create because it would have to pay attention to many things at once. On the other hand, if you're hierarchically extracting topics all the time from the input as you're going, you have very semantically accurate hierarchy of topics, which can be used for summarization questions like, what was section 3 about? And so they're complementary approaches that it's best to experiment with both.
Sure, yeah. I have all day. But you guys might eventually want to get lunch.
Yeah, folks definitely do want to get lunch, but I'm so grateful for your time. Let's take 2 more questions and let Guido and the rest of us get lunch. Let's take a question over here. Oh, someone has the mic. Sorry.
Yeah, I was wondering if you could talk a little bit about the schema for your database of knowledge nuggets. Like, is it better for the schema to be more general, or have you considered having, maybe representing more specialized types of knowledge, or?
The schemas we use, I'm not sure if you asked for the query schema or the ingestion schema.
The schema for the representing the knowledge nuggets.
Okay, that's the ingestion schema. The query schema is somewhat this sort of at arm's length from the knowledge representation, I would say. I can actually pull it up if I can manage to drag that window over again, which now I know. Well, I remember that. Look at that. So I can actually restart the app. This is actually going to show the other schema. I'm sorry, but this is going to show it. It will show this query schema. The other one, I would have to remember the file where it lives. But this, yeah, it scrolled off, of course, most of it. But here you get a sort of a general sense of what is in the schema. And so we try to use meaningful names for all the classes and fields, somewhat loosey-goosey types, and we add comments that sort of help the LLM understand how a particular data structure is to be used. So this is the main part of our prompt. And there's definitely a lot of tinkering that you could do with this. There's a similar one for the ingestion, but I'll skip showing that.
Thank you.
Can we take one more question?
Thank you for everything today, first of all. And my questions, 2 quick ones. So you're structuring this, you're showing your query, but are you still going to, and so that will go to a JSON, you'll retrieve from the data, but you make an API call or something, but are you still using an embedding somewhere in the journey? And then if you could share the email ingestion repository where we can find that early preview as well.
The only thing we use embeddings for is to find related terms. Like, and we don't need to use embeddings. We could easily use some other, maybe dictionary-based piece of software that can give us aliases like, I don't know how much I demonstrated that during the demos, but you can say, what did he say? What did he send? What did they send?
So a single numerical representation embedding for each value. And
sorry?
A single numerical representation instead of the entire graph, in other words, to save a lot of space.
Yeah.
Simple, yeah, okay. And then the email ingestion early preview, you mentioned, you teased us with the early preview of the email. Is it available, the GitHub repo?
Yes, I tried to show it. I think this one has it. Since it was my inbox, although my inbox apparently has like 95%. Oh, this is just ridiculous. Oh, it's all in the repo, is all I want to say, because I can't do it justice on this small screen. But it is in the repo, yeah. Type agent-py on GitHub, or type a. Yeah, I'll go back to the slide that has the resources, because there's an unfortunate naming difference. The wheel and the module you import are called type agent, but the repo is type agent-py because it has origins in a much larger project that is already called type agent.
Well, thank you, everyone. A big, huge round of applause for the creator of the Python language. An excellent talk.